Hello everyone. In this video, I am going to teach you about what is cutoff frequency of a waveguide. We know waveguide is like a channel for microwaves. It is used to pass the microwaves. Cutoff frequency is nothing but from which frequency the waveguides allows the microwaves for passing. Okay, that is known as cutoff frequency of a waveguide. In this video, I am going to derive how to calculate or how to derive the cutoff frequency of a waveguide and the cutoff wavelength of the waveguide also. Now let's see first this expression, that is, we know h square is equal to gamma square plus omega square mu epsilon equal to a square plus b square equal to m phi by a whole square plus n phi by b whole square. We already derived this equation in propagation of TE and TM waves in rectangular waveguide. I have already derived this equation in our previous video. If you don't know this equation, please watch our previous video and then come to this video. From this equation, we know if we if we move this term, that is omega square mu epsilon into this side, then it will become like this, that is gamma square is equal to m phi by a whole square plus n phi by b whole square minus omega square mu epsilon. And if we move this square to this side, then we can get, that is gamma is equal to square root of m phi by a whole square plus n phi by b whole square minus omega square mu epsilon. We know gamma is nothing but propagation constant. We know propagation constant is a sum of attenuation constant and phase shift constant. That is, we can simply represent the propagation constant gamma as alpha plus j beta, where alpha is the attenuation constant and beta is a phase shift constant. Okay, here observe alpha is a real part and beta is the imaginary part. Compare alpha plus j beta to this expression, then m phi by a whole square plus n phi by b whole square will become real part and omega square mu epsilon will become imaginary part. Here omega square is nothing but frequency. If we use a signal which is having the low frequency, then the condition is at low frequency, we know gamma is equal to root of m phi by a whole square plus n phi by b whole square minus omega square mu epsilon. At low frequency, this omega value will become low. That means gamma is approximately equal to root of m phi by a whole square plus n phi by b whole square. Okay, whenever at low frequencies, omega square mu epsilon is very less than m phi by a whole square plus n phi by b whole square, then we can say gamma is exactly equal to, or not exactly, approximately equal to root of m phi by a whole square plus n phi by b whole square. That is, gamma is equal to real part, not imaginary part. Here there is no imaginary part because this imaginary part value is very small. We can simply neglect this. That means alpha plus j beta, here beta equal to 0, that is gamma is equal to alpha. We know alpha is a attenuation constant. Here we have only attenuation, there is no phase shift. Only attenuation means the signal won't be allowed, the entire signal will going to attenuate. Okay, this is the condition for attenuation. Whenever our omega square mu epsilon is very less than m pi by a whole square plus n pi by b whole square, that means the total signal will going to attenuate. No signal pass through the waveguide, which means the waveguide act as a barrier. I mean, the waveguide cannot pass the signals which is having the low frequencies. Okay, observe here, gamma becomes real and positive and equal to attenuation constant alpha. Here we already know when beta equal to 0, then gamma equal to alpha. That means gamma equal to attenuation constant. That is, wave is completely attenuated and there is no phase shift, hence the wave cannot propagate. Here observe one more condition. If omega square mu epsilon is less than m phi by a whole square plus n phi by b whole square, then only the signal will going to attenuate. If suppose at high frequencies omega value is very high, then omega square mu epsilon is very high. That is, omega square mu epsilon is very greater than m phi by a whole square plus n phi by b whole square. Then our propagation constant gamma is approximately equal to the phase shift constant, that is j beta. Here attenuation is very small when compared to the phase shift constant, we can simply neglect the attenuation constant. That means here in this case at high frequency case, gamma is almost equal to the phase shift constant. Okay, that is, see here gamma becomes imaginary. That means here the real part will become zero, because here frequency is very high when compared to the real part. That is, gamma becomes imaginary. There will be phase change beta, and hence wave propagates. In this case, wave propagation is there because there is no phase shift here. Sorry, there is no attenuation here. Here only we have phase shift. There is no attenuation, means this signal pass through the waveguide. At the transition, alpha becomes 0 and the propagation just starts. The frequency at which alpha just becomes 0, it is defined as cutoff frequency. Sorry, here there is no alpha. Here we need to write gamma. Gamma becomes 0 and propagation just starts. The frequency at which gamma, here also we need to write gamma. This is a mistake. Gamma just becomes 0 is defined as the cutoff frequency. When we call the cutoff frequency, means whenever our gamma will become 0, then we can say that is a cutoff frequency. Okay, here also it is a mistake. uh, we need to write in place of alpha as a gamma. That is, when we call the frequency as cutoff frequency, that is f is equal to fc, means whenever our propagation constant, that is gamma, equal to 0, that is omega is equal to omega c is equal to 2 pi f. We already know what is the relation between omega and f, means omega is equal to 2 pi f. Both are frequencies, but omega is in terms of radians and f is in terms of hertz. Okay, let's see. Okay, we already know this expression, that is m pi by a whole square plus n pi by b whole square minus omega square mu epsilon equal to 0. Actually here not 0, here in place of 0 we have, here observe, here in place of 0 we have gamma in previous slide, but we already assumed whenever gamma equal to 0, then only we have what called cutoff frequency. Cutoff frequency starts when gamma equal to 0. So I simply put in place of gamma as 0. Then here I moved this omega square mu epsilon term to this side. Then it will become positive, and I moved this epsilon mu to this side. Okay, then our equation will become like this. That is omega. Here I simply write in place of omega as omega c. That is cutoff frequency is equal to 1 by root of mu epsilon into m phi by a whole square plus n phi by b whole square whole power 1 by 2 is nothing but square root. Here observe, we can simply represent cutoff frequency is in terms of hertz. That is fc is equal to 1 by 2 phi root of mu epsilon into m phi by a whole square plus n phi by b whole square whole to the power of 1 by 2. We know already root of 1 by root of mu epsilon means c. Here is there, c is equal to 1 by root of mu epsilon. Here in place of 1 by root of mu epsilon, I simply substituted c value, that is c by 2f into m phi by a whole square plus n phi by b whole square whole to the power of 1 by 2. Here I simply take phi as common in these two terms, then phi will become common, and this denominator phi and numerator phi will become cancelled. Then our final cutoff frequency is fc is equal to c by 2 into m phi by a whole square plus n phi by b whole square whole to the power 1 by 2. This is the cutoff frequency of waveguide. Okay, and we can find the cutoff wavelength of a waveguide by using this cutoff frequency. We know the relation between the cutoff wavelength and cutoff frequency is nothing but cutoff wavelength is equal to c by cutoff frequency. Okay, here we simply substitute in place of fc as this complete term. Then we can get expression like this, that is 2ab by root of m square b square plus n square a square. That is a cutoff wavelength. Lambda c is equal to 2ab by root of m square b square plus n square a square. This is the cutoff wavelength for waveguide, and this is about the cutoff frequency and cutoff wavelength of a general waveguide which is used to pass the microwaves. I hope you understood this concept. Thank you for watching this video, and please like my video and subscribe to my channel.